Welcome back to Daily Dose of Space. There is a number that quietly shapes the entire universe. It determines how fast galaxies move away from each other, influences how old the universe is, and affects every large-scale structure that exists. For decades, scientists believed that number was gradually becoming more precise with better instruments and improved observations. Instead, it has turned into one of the biggest problems in modern cosmology. The deeper astronomers look, the more this number refuses to agree with itself. And if that disagreement is real, it could mean that something fundamental in our understanding of the universe is incomplete. A constant that defines reality. The Hubble constant is meant to describe how fast the universe is expanding today. It connects distance and velocity in a simple way. The farther a galaxy is, the faster it appears to be moving away from us. This relationship was first discovered by Edwin Hubble in the 1920s, and ever since then, refining its value has been one of the central goals of cosmology. At first, the uncertainty was enormous. Early measurements were off by factors of 2 or more. Over time, technology improved. Telescopes became more powerful. Detectors became more sensitive. Statistical methods became more sophisticated. By the early 21st century, many scientists felt that the Hubble constant was finally settling into a narrow, reliable range. What no one expected was that improved precision would reveal a deep conflict instead of agreement. Measuring the nearby universe. One way to measure the expansion rate is to look at relatively nearby galaxies and determine their distances as directly as possible. Astronomers use objects known as standard candles, which have predictable brightness. Cepheid variable stars pulse in a way that directly relates to their intrinsic luminosity. Type 1. A supernovae explode with remarkably consistent brightness, allowing them to serve as cosmic distance markers across billions of light years. By building a distance ladder from nearby stars to distant galaxies, scientists can measure how far away galaxies are and compare that with how much their light has shifted toward the red end of the spectrum due to expansion. This method relies on well-tested physics and decades of calibration work. When this approach is applied carefully, it consistently produces a value for the Hubble constant that is noticeably higher than expected from other methods. The difference is not subtle enough to be ignored as random noise. It is large enough to demand explanation. Measuring the ancient universe. A completely different method looks not at nearby galaxies, but at the oldest light in existence, the cosmic microwave background. This faint radiation is the afterglow of the Big Bang, released when the universe was only about 380,000 years old. It carries a detailed imprint of the early universe's structure in the form of tiny temperature fluctuations spread across the sky. By analyzing these fluctuations with extraordinary precision, scientists can infer the composition of the early universe, including the amount of matter, radiation, and dark energy present at that time. From these parameters, cosmologists can calculate what the current expansion rate should be, assuming the standard model of cosmology is correct. This early universe method produces a value for the Hubble constant that is lower than the one measured from nearby galaxies. The precision of these measurements is extremely high, and they are supported by independent observations from multiple missions. The disagreement between the early and late universe measurements has now grown beyond what can reasonably be attributed to measurement error alone. When precision creates a crisis. At first, many researchers assumed the tension would disappear as data improved. Historically, discrepancies in astronomy often shrink with better calibration or larger data sets. Instead, the opposite has happened. As measurements have become more precise, the statistical significance of the disagreement has increased. Different teams using different telescopes and analysis techniques continue to arrive at the same conflicting values. The methods rely on entirely different physical principles, which makes it harder to blame the problem on a single systematic error. This is why the Hubble tension is taken so seriously. It is not one experiment contradicting another in a fragile way. It is two independent approaches, both internally consistent, refusing to converge on the same answer. The possibility that something is missing. If both measurement methods are correct within their own frameworks, then the problem may not lie in the data, but in the model connecting them. The standard cosmological model assumes a specific behavior for dark energy, dark matter, and the geometry of space-time. If any of those assumptions are even slightly wrong, the predicted expansion rate from the early universe could be off. Some physicists have proposed that dark energy might not be constant over time, but could evolve in subtle ways that change the expansion history. Others suggest the existence of additional types of particles in the early universe that briefly altered its dynamics. There are even proposals that gravity itself behaves slightly differently on cosmic scales than current theory predicts. None of these ideas has yet provided a fully convincing solution, but their very existence shows how seriously the community takes the discrepancy. Why this changes everything. The expansion rate is not just a number in a table. It influences the calculated age of the universe and determines how quickly structures like galaxies and galaxy clusters formed. A higher expansion rate implies a younger universe, while a lower one suggests more time has passed since the Big Bang. If the early universe measurement is correct and local measurements are biased, then something about our cosmic neighborhood may be affecting observations in ways we do not fully understand. If the local measurement is correct, then the standard cosmological model may require revision at a fundamental level. Either outcome carries significant implications for our understanding of cosmic history. Could our perspective be distorted? One idea that has gained attention is that our region of the universe might not be perfectly typical. If we happen to live in a slightly underdense region, sometimes described as a local void, the expansion rate measured nearby could appear faster than the global average. This would not require new physics, only a reevaluation of how representative our measurements are. However, evidence for such a large local effect remains debated. Observations suggest some variations in matter density, but whether they are sufficient to fully explain the Hubble tension is uncertain. This possibility highlights a deeper issue in cosmology, the assumption that our vantage point is statistically ordinary. If that assumption fails, even slightly, it complicates how we interpret the universe. The role of future observations. New observatories and missions are being designed specifically to address this problem. Improved supernova surveys aim to refine distance measurements. Independent methods, such as gravitational lensing and observations of neutron star mergers, are being developed to provide alternative expansion rate estimates. Each new technique offers a chance to confirm one side of the tension or reveal hidden biases. The hope is not simply to split the difference between two numbers, but to understand why they diverge in the first place. Whether the solution lies in better calibration, overlooked astrophysical effects, or entirely new physics, the coming decade will be decisive. A universe that resists. Final answers. For a period in recent history, cosmology felt almost complete. The standard model explained the cosmic microwave background, large-scale structure, and the acceleration of expansion with remarkable success. The Hubble tension has disrupted that sense of closure. It suggests that precision does not always lead to comfort. Sometimes, it exposes cracks that were invisible before. The universe is expanding. That is certain. But exactly how fast and why different methods disagree remains one of the most pressing open questions in science. Until those numbers align, cosmology remains unfinished, and the universe continues to remind us that understanding is always provisional.